All right. So get your notes out if you don't already have them out. And we're going to talk about scientific notation today. And we're going to do scientific notation, people, for a good reason. The numbers you're going to use in chemistry are going to be sometimes really, really big and sometimes really, really small. Okay? If you think about a really, really small number, if I'm talking about the mass of an atom, it's a really, really small number. It's going to be, if I had to write it down, it's going to be something like 0.000000000000000, and I'm not kidding, that many zeros or more to get the actual answer. I can't do that, and neither can you. It's too much of a pain. You have to be counting the zeros all the time. So what do? We use scientific notation, which you all had at some point or another in your math classes. That's just where you multiply by 10 to some power, right? Right? Okay, you've all done that. Now, just before I get started, let's just do a couple of quick examples, because there's a lot of mistakes we get made. All right, like if I had 24000, what would that guy be in scientific notation? Wait, raise your hand. See what you think. Because I might get more than one answer for this. I don't know. 24000. That's 24,000. What would that be in scientific notation? What do you think then? 24 what? 24.3. 243?
Small 3.
Small 3. 24, 2 to 3. That's a great mistake. I love that one. It's not one I was expecting, but definitely a great mistake. What's wrong with that? Plug that into your calculator. See if 24 to the third power is the same as 2,400. It ain't. You don't have to do it. I was just kidding. That was rhetorical. All right. So that's one mistake. It is not raising to the third power that number. So no chance here. But what do you think?
24 times 10.
That's more of what I expected for the wrong answer, and it's still wrong. It's not technically wrong. I mean, that does equal this. But it's not technically in scientific notation. What do you think?
2.4 times 10 to the 4th?
Absolutely. So it took a little while there to get that down, and I'm glad I got all those mistakes. The only mistake I didn't see, and I expect that sometime or another, is if I have, 0.00024, or something like that, where people will have the wrong. What would I have to do for that guy? What would he have to be? 2.4 what? Times 10 to the, yeah, you may have to use a positive or a negative exponent, okay? So that's the other thing I was expecting, maybe to see a mistake on the sign. But absolutely glad I did that, because I'm surprised, but I got those mistakes, and that's what you don't want to do. Now let's talk about how you do it. Now, I know most of you guys have been taught this before. I may teach it a little bit differently, okay? I'm going to pretty much, again, try to avoid the memorization that you've had to do for most of your life on stuff, and try to stick more with the, a process instead of memorizing. And common sense. Process and common sense. You don't need to use as much of your brain power to memorize garbage, which you guys have always done. Left, right, positive, negative. That's what you're going to be answering when I ask you in a minute. And I don't want you to do that. I want you to just think about it. You can figure it out. So here we go. First of all, the purpose. As I mentioned a minute ago, scientific notation is going to be used in chemistry because we deal with some really big and really small numbers. Very small numbers, like when we talk about the mass of an atom. Very large numbers when we talk about how many atoms there are in a mole or in something else, some amount that you could actually see, because we don't really see an atom. It's too small. So we have really big and really small numbers all the time. And we don't want to have to write them all out. So we use powers of 10 to do this. All right, so let's do this. 3 steps. 3 basic steps to convert into scientific notation. Well, the first one is a mistake we made actually, you both made, 2 people made. You got to move that decimal, not just to the end of the number, but rather so there's only 1 digit to its left. Okay? You're going to move the decimal so there's only 1 digit to its left. You just don't move it to the end of the number, like 24. times 10 to the something. It's got to be 2.4. You do that for a reason, because a lot of times we have very, very large numbers, that a lot of which have the precision to measure. Like it could be 2, 4, 7, 9, 5, 1, 3, 4. I don't move it to the end of that and then have to still count decimal places a lot. I want to always have just very standardized one number to its left. Okay? That's the first thing you do. Of course, then to find out how many zeros you're going to need, what are you going to do? How many zeros are you going to have? How will you know after you move that?
However many there is.
Not however many zeros there are, but however many,
Numbers.
not numbers, however many, what's the word? Because like say for example, let me show you. Say for example, I have 2, 4, 3, 0, 0, 0. I don't, like you would want to do, say, oh, I'm going to have an exponent of 3 because I have 3 zeros. I don't go by how many total numbers I have. I go by how many places I moved it. How many places I moved it, okay? All right. Count the number of decimal places moved to determine the exponent of 10. But another good mistake, you don't just count the zeros. If you were doing it your old way, you would have, but that's not standard. Then sometimes you'll have 2 numbers to the left, 3 numbers to the left. You never know. You got to have a standard way of doing these. Now this last one is where I'm really going to go off the rails here and not just have you memorize. Here's if I ask you, I bet you all will tell me the same answer. Okay? I moved it 1, 2, 3, 4, 5 spaces, and now it's 2.43 times 10 to the 5th power. If it were this, 0.000243, where would I move a decimal? 1, 2, 3, 4 spaces, right? Okay, so it would be 2.43 times 10 to the 4th power, right? Oh, it's negative. All right, okay. How do you know? How do you know this guy's negative, that guy's positive? What's the answer? Okay, I'm getting better answers, but because a lot of people, we know what I normally get? Well, because I moved it to the left, it's positive. Because I moved it to the right, it's negative. All right? I hate that answer. That's a terrible answer. What I heard out there was better. People trying to explain how you're making the number bigger or smaller or whatever. You know what I'm going to try to, know how I'm going to explain it? With 2 lines. What do those 2 lines mean? Equals. The 2 numbers have to be equal. So I'm going to be very vague. I'm going to be deliberately vague on number 3. Number 3 is going to say just assign a positive or negative sign to the exponent. This will take into account a lot of things that you wouldn't take into account by just positive, negative, left, right, whatever you want to memorize, as you'll see in a little bit. Okay? So let's try some of these. You ready to do some examples? Using my method, and you can try it on your own as we do each of these. Try that guy. Hey, you know what? I didn't even look at the number. Is that the number I was writing down, or was it 248?
No,
That's just your brain. That's like your brain being freaky because I never saw that number. I had no idea that was what's going to pop up. I just wrote it down. That's weird. And you're the first class to do it. I didn't do it in your class. That's really weird. So, what do we do here? Let's take a look. I'll move this guy over 1, 2, 3, 4, 5 spaces. Y'all agree? 2.43 times 10 to the 5th power. Y'all get that, I bet, right? You know what's a really useless thing to do here? Is people, we're going to get some large numbers, lots of zeros. People will do this, 2.43000 times 10 to the 5th. What's the point of doing that if you're going to keep all the zeros? What was the whole point of using scientific notation? So we don't have to write all those zeros, those placeholders. You see what I'm saying? Okay, so 2.43 times 10 to the 5th. There's another reason that's wrong, actually. It's not just a bad idea because you're wasting time. Why is that now wrong? Exactly. I just created, by doing this, I created 3 extra significant figures because that guy's got 1, 2, 3, 4, 5, 6. This guy's only got, without this here, remember, this guy's only got How many? 3. Okay. All right, let's do the next one. 0.0079. Try that one on your own. See if you can make some mistakes here. I want to see some mistakes in these examples. In the past, I'm sure someone was going to call this 79. You're not going to now, right? 7.9. How to move it? 1, 2, 3 spaces, correct? All right, times 10 to the what power? Did you all put -3 there, right? Okay, good. Try this one. Some of you are saying to yourself, well, it's already in scientific notation. Or are you going to convert that into standard notation? I want you to convert that into scientific notation, and I didn't misspeak. It is not in scientific notation yet. Yes, it is. No, it's not. What's wrong with it? This guy, decimal, look where he is. Going to have to move him over 2 spaces. 4.83 times 10. Now here comes where my system beats yours of memorizing left, right, positive, negative. Common sense. What does this thing mean? It means equal. It means this has to equal that. Now listen carefully to this. 483 does not equal 4.83, does it? This guy's a lot smaller than this guy, right? So guess what I'm going to have to do to that exponent to make them equal again? What am I going to have to do to that 10 to the 4th?
Make it negative.
No. Make it bigger. I made this guy smaller by 2 spaces. Do y'all agree I did that when I made it from 483? Oops. When I went from 483 to 4.83, I made this number smaller. But they still have to be equal. So what will I do? I have to make him bigger. And by how many places? 2. So it'll be 10 to the 6th power. You see, here's where your left, right, positive, they're both positive. A 4 and a 6 is positive. The question is, common sense tells me to keep them equal what to do. Let's try another one. Try that one on your own. See if you get it right. I'll know you understand if you do. But I have a feeling a lot of people won't. Everybody get an answer for that. I don't want to write the answer down until everybody has something down. Because I want you to make a mistake. Make it now so we don't make it later. Let's see. Well, first off, do we move it to the right spot? 1, 2, 3.9. 3.9, everybody got that? All right. Okay. Times 10 to the. Now let's use common sense. Again, even using common sense, it can be confusing. Watch. What did I do to that number? I made him what? Bigger. By how many places? 2. But they have to be equal. So I have to make this guy what to keep them equal? Smaller. By how many places?
2.
What is -5 smaller by 2 places?
7.
-7, not -3, which I bet some people have there. Oops. I'm sending -3. Okay? See some erasing. See? These are not, as easy, even though you've had them before, they're not as easy as you think. Oh, I wanted to go back and do something else here. That was the last example I had of those. Let me explain to you something else, too, about the, 2 things. I want to use a number line. Okay? Let's use a number line. And we'll hope to explain 2 things. Start out with that -5 and -7. Here's your number line. Here's 0. Here's -5. Here's 5. Here's 10. All right. How do I make this guy even smaller? All right, I had to make him -7. And -7, isn't that a bigger number? No, it's not. It's a smaller number. It's further away from 0. But here's the bigger thing I wanted to show you. That was just to answer the other one. The bigger reason I wanted to put a number line up here is to show you why all this works. When you're multiplying by, oops, what did I do? Here we go. When you're multiplying by these exponents, what are you really doing? All right, here's 0. Here's 10. Here's, let's call this guy 100. Here's negative 10. Here's negative 100. Let me ask you, on the number line, where is 10 to the second power? Well,
100.
all right, this is 10 to the second power. Everybody agree with that? Good. Where's 10 to the first power? Trey. 10. Everybody agree with that? Where's 10 to the negative second power? Where do you think 10 to the negative second power is? Emily?
Negative 100.
Negative 100. And 10 to the negative first would be right here, right? No, actually, not at all. They're both completely and utterly wrong. I skipped over one on purpose. What's 10 to the 0 power? You all know that one. Yeah, everybody knows anything to the 0 power is what? Not 0. Anything to the 0 power is what? 1. So basically 10 to the 0 power is right here. It's at 1. Okay, there's 1 right there on the number line. You know where 10 to the negative first power is? It's, I'm going to make my line a little smaller here. 10 to the negative first power is right there. You know where 10 to the negative second power is? Right there. You know what 10 to the negative 185th power is? Because what does a negative exponent mean? Yeah, it means the reciprocal or the fraction. In other words, hold on. In other words, 10 to the second power is 100. 10 to the negative second power is what? 1 over 100. So it's a fraction between 0 and 1. Now, does that help to explain why the equal sign? Let's talk about the equal sign again. Okay, let's look at these numbers again. Right? These guys have to be equal. Here, I'm taking 7.9, and I'm multiplying them by 1 over 1,000. When you do that, you're multiplying by a fraction, right? What are you doing to that 7.9? Making him smaller by 3 spaces. Same as I just explained to you when we did metric conversions, right? What is 7.9 made smaller by 3 spaces? 1, 2, 3.0079. See, when you multiply by a fraction to the negative power, when you multiply by a negative power, you're multiplying by a fraction, by 1 over 100 or 1 over 10. All right, enough of that. Now, I want to talk to you about actual multiplying and dividing and doing calculations with